All right. Well, thank you everyone for joining us for this week's Exoplanets seminar. And I want to thank Dr. Kim Bott for speaking with us today. Dr. Bott completed her PhD at the University of New South Wales in Australia, working with Jeremy Bailey. And then she started working with Vicki Meadows as a postdoc at University of Washington. And just after the pandemic broke out, she switched over to UC-Riverside, working with Stephen Kane. So with that, I'll turn it over to you.
All right, thanks, Joe. So I'm very happy to be talking to you all today. Thanks for having me. I'm going to be talking about how I apply my speciality of polarimetry at first primarily to hot Jupiter type exoplanets, and then towards the end of my talk, I'll delve a little bit more into smaller, cooler worlds. So I thought I would start out with a little bit of background to polarimetry. I know a lot of people do not use polarimetry in their day-to-day work, and many of us probably had courses in undergrad that didn't even cover polarimetry. So just to get us on the same page, I like to conceptualize polarimetry of thinking of light as a vector. So when we think of light, we have these aspects like its wavelength and its intensity. And there's this additional aspect of the polarization, and that's the preference in the direction that the electric field oscillates. So we would start out with an unpolarized source, like an ideal star, maybe something like the sun, something producing unpolarized light, and that light has an electric field vector that oscillates in any and every direction. It doesn't have a preference. And then in interacting with a surface and reflecting off of water or scattering through an atmosphere, that can impart a preference in the way that the electric field oscillates, whether that's up and down or side to side or in a corkscrew. So when we think of phase curves as a planet is going around its star, if we're seeing something edge on, we expect that as the planet moves around to full phase, that it just gets brighter and brighter and brighter and then becomes dimmer as it comes back around into crescent and new phase. If you're looking at a polarized light curve, if you have a planet with just Rayleigh scattering happening, then you expect your strongest signal to actually occur closer to quadrature. So if you're looking at the full phase curve of the planet going around its star, it's more of this kind of M shape or McDonald's arches shape. We of course have things in addition to Rayleigh scattering to consider when we're talking about our phase curves, particularly in polarized light. Some other features are particularly strong polarizers. For example, rainbows are very good polarizers of light. And if we take data, if we take a phase curve for a planet in different wavelengths, we can work out a lot of information about what the condensates are on that planet. And that, of course, was used famously in our own solar system to characterize the Venus. Clouds and hazes can produce other optical features in your polarized light curve as well, additions to Rayleigh scattering, backscattering and glory effects, things like that. And of course, we have our Rayleigh scattering. That's a very effective polarizer of light. And once again, if we're just considering Rayleigh scattering, then we have this sort of M-shaped curve to our phase curve for the planet. And we can also consider if we can see a surface on a planet, things like the ocean glint, that's a particularly strong polarizer of light, and different surfaces will polarize the light in different ways. We also have chiral molecules, pigments, things like that, that can polarize light. I'm not going to be talking about that today, but I have done a little bit of work related to that. So if you're interested in that sort of thing, I'd encourage you to reach out to me or maybe talk to me after. And in addition, we have other benefits to using polarized light. If we know that the planet's signature is going to be dominated by Rayleigh scattering, that we should expect that sort of M-shaped curve, then we can back out information like the inclination and eccentricity of the orbit from the relative shape of the curve. So if we know something about the atmosphere, we could work out orbital parameters. And finally, if we have a main sequence quiescent star, the starlight should be suppressed. So that should be a poor source for polarized light. So it's a great way to get a kind of differential signature, knowing that the photons that you're getting that are polarized should be from your planet, from something scattering or reflecting the light, and not from the star. So I like to think of this in terms of how polarimetry complements and adds to other methods that we use to characterize planets. So I've already kind of touched on the things highlighted in green, and you can see there that you get a slightly different signature for things like ocean glint, if you're looking in polarized light versus if you're looking in unpolarized light. Polarimetry, of course, is used in direct imaging and secondary eclipse for emissions. There are a lot of people in California actually working on projects related to trying to detect polarized light in emissions from brown dwarfs and young planets. Template matching is also done in polarized light. So there are polarimeters like Spiru that do high resolving power spectral polarimetry for template matching or cross correlation technique. Rotational mapping can also be done in polarized light, and there might be some benefit there in getting slightly more specific information out of your phase curves to produce a map of a planet. And transits as well can also be done in polarized light, and that's been performed in our own solar system, and including for Earth using lunar eclipse data. But there are some great papers from Sengupta et al. And Kostigers, I'm sorry if I'm mispronouncing that name at all, showing how that technique in polarized light could be used for exoplanets. So how would we apply this to observations of hot Jupiters? Well, we have these early predictions around the turn of the millennium for the reflected light from exoplanets, what type of signals and the intensity of the signals we should expect in polarized and unpolarized light. And the kind of seminal paper is the Seeger et al. Paper from 2000. And in this paper, these are somewhat idealized models, and they are only considering the Rayleigh scattering from the atmosphere, but they predict signals in the tens of parts per million for a planet unresolved orbiting its star, a hot Jupiter type planet, something big reflecting a lot of light very close to its star. And so the models that they're using in this are Rayleigh-Lambert models. So you're just treating the planet as a Lambertian sphere and only considering as the Rayleigh scattering coming from the planet. So you're not including cloud effects like the rainbow and things like that. And they do compare in the paper these models to a more full radiative transfer model, and found that the discrepancies were relatively small, just at the parts per million level. But you'll see throughout this talk why we might actually want to be using these full radiative transfer models to match data and produce predictions for polarized light from these planets, because these tens of parts per million expected signals, as I said, are quite optimistic, and it turns out that maybe we don't see that in most cases. So modern polarimeters, though, are already sensitive to the parts per million level, and new polarimeters are being built with even greater sensitivity right now. So we certainly have the equipment that should be able to detect these types of signals. So I thought I would take us through a little bit of the history of the planets that have been, there have been attempts to detect the polarized light from. So there's only a handful that I'm aware of that have been looked at with high precision polarimeters, like parts per million sensitivity polarimeters. And I'll talk a little bit about who observed each planet and some possible issues that might have stopped the groups from detecting a signal in each case. So first we have the 55 Cancri system that was observed by a British group with the planet pole polarimeter at La Palma. And La Palma, you'll see me bring this up a few times, is affected by Saharan dust. So that's certainly something to consider anytime that you see observations happening there. Of course, this is also a multi-planet system, which is just inherently more difficult to pick out phase curves from. I believe the reason that this was one of the first exoplanets where polarimetry was attempted is because it was one of the ones that had, or one of the first systems. It was one of the systems that was, that had predictions in the Seeger et al. Paper. So this was a non-detection for the system, but for 55 Cancri E, at least, they were able to give a upper limit to the albedo. So at least a little bit of science came out of that. Next, we have Tau Boo. The same British group also looked at that, as well as an Australian group with the HIPPY-2, or the HIPPY and the HIPPY-2 polarimeters. And this group is kind of an offshoot of that British group. Jeremy Bailey used to be part of the Planet Pole group and then built his own polarimeters after moving to Australia. So HIPPY was meant to be more sensitive in blue light than Planet Pole was to detect these Rayleigh-dominated atmospheres and polarized light. Both campaigns produced non-detections though, upper limits to the albedo. So once again, we have a non-detection for that. Next we have HD179. That was also observed by the Australian group, also produced a non-detection. And for this planet, I just want to take a little detour into talking about how we consider stellar noise and the interstellar medium. That's something that should be considered in all of these planetary observations, and they are to varying degrees for each set of observations. So for stellar noise, that's if you're not interested in the star and you're interested in the planet, the stellar noise is just noise from activity. The interstellar medium should produce a constant polarization. And so in your actual data, that will look like an offset from 0 that your modulation and your signal then moves around. So the way that we characterize this in our upcoming paper is we take a kind of general look at the activity of the stars and the systems that we were observing. And you can see HD179 there is sort of a moderate, not terribly active star, but it was something that we still wanted to consider. And you can probably see in that table a punchline for something I'm about to bring up in a couple more slides. For the interstellar medium, by Daniel Cotton in Australia, that is sort of mapping the interstellar medium's polarization for the nearby interstellar medium using stellar observations. So with that, we are kind of looking at how stars in a general area at a given distance, general area of the sky at a given distance, tend to polarize light. So what is the contribution that we would expect from the interstellar medium? And then we're independently fitting that offset when we're fitting models to our data, and then just comparing those to see if they're similar numbers, and they tend to match pretty closely. Next, we have WASP-18, observed by the Australian group. For this, we got quite a bit of data fairly early on in our campaign. So we were able to produce an upper limit to the polarization and the albedo. And from this, we were able to do a little bit of science. So that was kind of satisfying. We were able to rule out certain cloud scenarios. So we could rule out a high scattering, Rayleigh scattering haze in the atmosphere, at least, just from the upper limit that we were able to produce. Oh, and I wanted to mention the reason for non-detection in this and probably in many of these planets is just simply that the signal is quite low. So at the time that the Seeger paper came out, we didn't really understand that these hot Jupiters often actually have quite low albedos. And although your albedo doesn't necessarily determine your polarization, if you have a very high polarization but a low albedo, you're simply just not going to get enough photons to detect that polarization. So the fact that hot Jupiters tend to be quite dark is probably problematic for most of these planets. So next we have HD 189. And if you've heard of any planet being observed in polarized light, it's probably this one. It's been observed by a few different groups, by an, at the time, European group, the dipole and terpole polarimeters, by an American group with the Polish polarimeters, and by the Australian group with the hippie polarimeters. So this early on had a very high detection from the European group, a very high detection of very high polarization from the system. And in follow-up work from that same group, they reduced the level of polarization, but it was still something very high. It was, you know, around 100 parts per million. So really just at the maximum that you might expect from any hot Jupiter. It would kind of be an extraordinary case if that was the polarization. And in follow-up work then from other groups, from the Polish group and the hippie group, those groups were not able to reproduce those levels of polarization from the system. So they had non-detections that produced upper limits to the albedo and the polarization. We now believe that the signal from that system is probably coming primarily from the star. So it's actually quite an active star. It's a BY Draconis variable. And you probably saw on the table earlier that compared to the other stars in our most recent paper, that it's quite a bit more active with a strong magnetic field. So it's probably got a lot of Starspot activity going on, and that's producing our polarized light signal. So as I said earlier, you need a kind of quiet star to be able to use this as a annulling effect for your starlight and know that the polarized photons you're getting are purely from the planet. And sorry, I have like things on my screen that are covering up the words, so I don't see the prompts that I normally have. Oh, right, and then the La Palma dust. So we do know that some of the early observations from the European group were probably also affected by dust storms in the Sahara. The times that they were taking the observations coincided with some strong dust storms. So I saved the best for last. If you were getting depressed about non-detections, we have a possible detection, just a 2.8 sigma, possible detection for 51 peg, finally. Possibly. We're hoping that in follow-up observations we can really pin this down. So we have a 2.8 sigma possible detection for 51 peg in our upcoming paper with a best fit to the modulation of for this type of planet. Just to show what that data looks like, I have on the right here the 51 peg data from the hippie campaign, and then on the left the quite noisy data for that kind of active star system for HD 189. And so the 2.8 sigma is for a detection of the polarized light from the planet, not necessarily for the 11 parts per million being exactly right, if that makes sense. So there's some confidence in the fact that we've detected polarized light from the planet, and it's just our best fit with a Rayleigh-Lambert model that it's a modulation of 11 parts per million. So where do we actually expect to see a strong signal? Can we predict these hot Jupiter planets are likely to be the best candidates for detecting the polarized light? As I said earlier, albedo is part of the equation. How many photons can you get from that planet? But it's only part of the equation. So Venus, for example, in our own solar system, has a very high albedo, but is a rather poor polarizer of light compared to Earth. Some other things we need to consider are the multiple scattering. You can imagine if you have an unpolarized source interacting with an atmosphere, if it's scattered few times or singularly, that is likely to impart a polarization. But if it's kind of ping-ponging around and being multiply scattered, that's going to randomize the polarization, and you're going to end up with a net unpolarized light signal by the time the light re-emerges from the atmosphere. And that, of course, related to your cloud top altitude. So you can expect that if you have a longer path for a cloud lower in the atmosphere, that you're more likely to encounter multiple scattering. So that's also something to consider. If that's of interest to you, there's a great paper by Thomas Fauché and Loke Rossi and Daphne Stam looking at using this fact to along with molecular absorption lines, to pick out your cloud top height and to discern that from the surface, at least in cases where you expect to have a dark absorptive surface, like on an ocean world or an Earth-like planet. We also need to be considering things like, is this going to be a liquid or solid condensate? Solid condensates, depending on how they crystallize, their structure can be very good or very poor at polarizing light. And hazes as well. They, of course, have been used to characterize worlds in our own solar system, but the way that the haze forms can dramatically affect how good they are at polarizing light. So that's something else that could be considered in our models. So if we're just considering 51 Peg, for example, the planet that we possibly have a detection of polarized light from with a recent hippie campaign, I have here just some early pressure temperature profile predictions for the planet. And then in the bottom, plotted in a spaghetti plot, if you haven't seen this sort of thing before, it's a pressure temperature profile in black, and then condensation curves for different species that might produce clouds in the atmosphere, and where it crosses is where you expect a cloud to form. So I also didn't realize that I had chopped off the top of the curve in this view. But basically for 51 Peg, as you move into the upper atmosphere, it kind of skirts this line for Na2s. So depending on whether or not that line crosses it, whether or not you have a cloud forming from that species, that might affect your polarized light signal for the planet. So if it has a very high cloud made from that, then that might produce a very strong polarized light signal. So looking at ever smaller and cooler planets, if you're into those sort of things, we can start to think of how we would expect the polarized light signatures to look from those sorts of worlds. So we can start out with an example of a sub-Neptune that I was doing with a student at the University of Washington, Lion Gez. GJ1214 is expected to have zinc sulfide or potassium chloride clouds fairly high up in its atmosphere. So we took a look at how different the signature from that planet would look depending on whether the zinc sulfide or potassium chloride clouds were the top layer of cloud in the atmosphere. The optical properties of those two species are pretty different, especially at short wavelengths. So I have the refractive index in that plot on the left, and we're just zoomed in to look at the values for the imaginary part of the refractive index, the attenuation. And you can see that it's much higher for zinc sulfide at short wavelengths than it is for potassium chloride. And we can see when we plot the phase curve for this world with those two scenarios and different size particles, not the right word, different size droplets, that we end up with different phase curves. So as you would expect, we get a very low signal from zinc sulfide with its dark absorptive clouds. With potassium chloride, depending on the size of the droplets, we can get something akin to a rainbow or a strong backscattering signal that's almost at the level of the current sensitivities of polarimeters. So as we move to even cooler worlds and things that are more Earth-like, we of course move into the realm of different condensates. So as I said earlier, whether or not these condensates are going to be solid or liquid is something to consider. We do have some liquid condensates for hot Jupiters, but we of course have additional things to consider like liquid water clouds as we move to cooler and cooler temperatures. So for terrestrial planets, true terrestrial planets, we'll definitely want to consider our rainbow contributions, the contributions of hazes and clouds, as well as the Rayleigh scattering. So that means that we really need a full radiative transfer treatment that's going to include these additional effects from the clouds, including the rainbow. And in cases where we think we may be able to see a surface, we'll need a full treatment for the surface. And there simply are not that many models that include those treatments right now. There are a few, and they're mostly based on the VLI DORT code, which certainly has areas where it could be further improved. This is a very useful metric for terrestrial exoplanets if we do get to the point where we can measure this sort of signal. As I alluded to earlier, Venus in our own solar system has quite low polarization. It has a very different polarization signature from Earth. And just kind of a cartoon comparison here of looking at a couple different wavelengths at Earth or a water world versus a Venus-like planet, getting a much higher signal from the Earth-like planet. As a more specific example, this is a model of a water world, in this case orbiting Proxima Centauri. So the numbers on the y-axis are going to look pretty dismal because this is going to be in the habitable zone of a red dwarf. So they're going to be quite small numbers. But just to show the sort of science that we could do with this, you can imagine getting a few different wavelengths in polarized light, a few different band passes in polarized light, and possibly looking inside and outside of a molecular absorption feature. And from the relative height between your rainbow and your Rayleigh scattering, getting some idea of the cloud heights and the cloud top height, and comparing that to what you see looking inside of the molecular absorption feature. Where your rainbow is occurring, the angle that that rainbow occurs, and how it changes in different wavelengths is going to tell you what the species is. Bit of science to be done if you are detecting cloud, and if you have these models to compare to that are including the cloud effects. And if you're seeing a surface and you're looking in redder wavelengths, you're likely able to detect things like the ocean glint from a planet. So this is a water world with cloud and Rayleigh scattering and all of these things included. So as I was making these models over the past few years, I became acutely aware of the areas where they could be improved, and I began speaking to other people who do polarimetric modeling, particularly for smaller and cooler planets. And in particular, I started to talk to Theodora Karolidi, who has one of the most capable and robust models in the world. And talking to her about how her model could be compared to the model that I use, V-Star, that was developed by Jeremy Bailey in Australia. So we put in for a Roses grant and actually won that. So I'm very happy and proud of that. So we've won the grant to do things like parallelize the code so that they can run even faster. There's a lot of computation happening, especially if you're including polarization and polarization of surface effects and clouds. And especially if you're wanting to do full phase curves and spectra, that's a lot of computation. So this work is already started on the HIAC supercomputer in Washington State. We're of course wanting to compare and vet our two codes. We, to our knowledge, have two of the most capable codes for the polarization of light in a full radiative transfer treatment in the world. So we are wanting to update both of them and compare them to each other and vet them against data. We want to adapt them for 3D output. So both models are capable of producing a 3D output. We just need to, V-star in particular, it needs to be adapted to take a spatially varying, what I'm calling 3D, a spatially varying input to include things like continents and horizontally heterogeneous cloud cover. As I've brought up earlier, we want to improve the inputs for things like surfaces and clouds to treat additional cases of solid clouds and haze type clouds, and to include work on the way that different surfaces polarize light. So in that little image there with the kind of rainbow colored dots, that is taking data from Earth observations with a polarimetric satellite and looking at the average way that different surfaces scatter the light. But even if you really dive into the literature, even within these subcategories like snow and ice, different types of ice can actually polarize light in very different ways. So that's something else that we want to incorporate. And then of course, we want to then take our new, even more capable models and apply this to producing predictions for the polarization of different types of exoplanets to guide not only these small and expensive polarimeters that are being developed by these groups in the US and in Australia, but for the 30-meter class telescopes that are considering polarimeters and space-based concepts like LUVOIR that will include a polarimeter and possibly with some tweaking be able to detect some of these signals. So with that, I'll leave you with my main takeaways and take any questions that you might have.
Thank you so much, Kim. That was a great talk. So if anyone has any questions, feel free to raise your hand. I saw that there was a question from Chris Stark. Chris, do you want to ask your question? Do you want me to read it?
Yeah, I can ask it. That's fine. I actually have a couple questions now. This was a fantastic talk. I really appreciate it. So something that I've been thinking about years ago was how a clumpy disk structure could affect the transit signal. But listening to your talk, I started thinking how it would affect the polarized light signal. And so I'm wondering if you've thought about how the dust in the system would impact the signals you're looking for. And the note I made in the comments here is that some of those planets are outside the dust sublimation radius, so that they could be impacting the debris disk and causing structures and things.
So I don't know a whole lot about that. I know that there's a little bit of work from the Australian group, and I believe from some European groups as well, looking at the polarization of disks and assuming some level of uniformity in there. I'm not really sure if anyone has looked in any depth at how a clumpy disk would look in polarized light. I do know, I believe Daniel Cotton actually started writing a paper, and I think he just ended up not submitting it, on kind of the stage where you have like a planetesimal with a cleared path moving through a disk. And that's about as far as I'm familiar with that. Sorry, I don't really have an answer to your question.
That's fine.
And does anyone else have any questions? Chris, did you say you have another one that you want to ask?
Sure, I can. I guess this question is more about the physics of rainbows, which you showed these strong polarization effects in the rainbows. Is that due to the spherical nature or the fact that it's a liquid? Can you get that same effect with a water ice particle? Can you get it for something that's not quite spherical, that's ice?
So for solid ice, it's my understanding that just the behavior of the polarization is very different. You're not producing a rainbow, obviously, but you can be producing polarization. So it's just that there's different physics happening on the surface. And to my knowledge, those features, at least for water, don't tend to be as strong, at least in visible light. They might be in other wavelengths. So, and to answer the other part of your question, if you have droplets that are maybe just slightly aspherical, those should still be polarizing the light. It's not from the shape of the droplet that the polarization is coming, but it is from the shape of the droplet that your rainbow is coming. So you might have a diluted signal because you're considering both the polarization of the light and the intensity of the light when you're like actually measuring the signal. So that might complicate things, I guess, is the short answer to your question. It might make it a little bit more difficult, but you could still get a signal.
Thanks.
And does anyone else have any questions for Kim? I have a quick one. This is probably naive, Kim, but with this new project that you're working on, combining all these different new models, is that solely looking at habitable worlds? Is there any sort of limitations on terms of like the upper ends of the thermal conditions on a planet that they would be able to support? Like, are you looking at exotic clouds or just H2O?
We're looking at exotic clouds. So both of our models are potentially capable of treating any type of cloud, and it's just a matter of how accurately it's doing that. So if you have like a solid cloud, I don't think that the treatment for that is particularly good in either model right now. But yeah, definitely more exotic species other than water can already be included in either model. But I mean, technically for habitable worlds, like we applied to the Roses Habitable Worlds program, but
Yes,
there
sure.
are benefits to modeling all types of planets, because this is just going to make it even more robust for also doing models of hot Jupiters, and more robust for doing models of solar system icy moons.
Great. That's very cool. Well, if no one else has any other questions, I think we will end there. But thank you again, Kim, for talking with us today. That was a really great talk.
No worries. Thanks for having me.